Okay, so good morning, everyone. Let me just start by recalling what we were doing yesterday. So we were interested in proving a semi-parametric Bernstein-von Mises theorem. Okay, so we proved such a result. Okay, for some functionals, real-valued functionals from our parameter space into R. Okay. And the prototypical example we had in mind was a linear function, right? Okay, something like this. And one thing I'd like to note, because it will turn helpful today, is that when we did the proof, a key point in the proof is to control the Laplace transform of this quantity. We want to show it goes to a Gaussian. So we had this Laplace transform of the Gaussian here, okay? And here we had some remainder terms that we wanted to show, that we have shown that they converge to 1 in probability, okay? So recall there was this part which came from the remainder terms in the line expansion, and then this ratio, using conditions, what we call condition C, which we interpreted as a change of measure condition in the prior. This in color, we could show it just goes to 1 in probability. Okay, and what I wanted to say is that with a little extra work, often one can show a slightly more precise result. One can show a non-asymptotic result. Okay, so something in the form. So here you'll have still the Laplace transform of the Gaussian, but you can actually often quantify this thing here. So often you are able to show something like this. So exponential delta, which depends on epsilon n, say the rate of convergence of the posterior to the true function in a certain norm. And you are able to quantify this with this sequence being itself a little O of 1, and this on an event of high probability. Okay, so on an event, say an prime of high probability. Okay, and this is helpful if you want to control things uniformly and not only asymptotically. Okay. So this was just a technical point from yesterday that I wanted to, I didn't have time to mention that yesterday. Okay, so let us conclude on this chapter on semi-parametric functionals just by saying, so we saw an example of the application with the Gaussian process priors, okay? So then we can apply it in the notes. I have an example with a linear functional, and depending on the smoothness of the functional, so on the smoothness of this representer here, on the true smoothness of the function of the true function f naught, and on the smoothness of the Gaussian process, you get a condition mixing these three smoothnesses that gives you sufficient condition to get the semi-parametric BVM. Okay, so I'll skip that. It's in the notes. Let me just conclude this part by noting that we can also have result for tempered posteriors. So remember, tempered posteriors is just similar to the posterior, but where I raise the likelihood to a power alpha. Okay. So here if I write the posterior mass, so the tempered posterior mass of a set B, it is just this, okay? So we just write to a certain power. So we saw in the first week in the rates part that the tempered posteriors, they were, we believed that they were characterized, they had a rate characterized by an effective sample size n prime equals to n alpha. Okay, and we can actually prove results, semi-parametric type results also for those tempered posteriors, which confirm this kind of prediction we had from the race. I didn't make it very formal, but I told you that in examples that was the dependence in alpha that we got. Okay, so here alpha may depend on n. Okay, can be an alpha n between 0 and 1. Okay, so I'll not give the full statement, but under similar conditions as before, okay, we can get also SP BVM type results. So not exactly. So there will be an alpha in there. So namely, so if we consider this shift that we use just as a technical device to put the posterior on the same on the good scaling, so we get something like this. So we have we can show that the alpha n posterior rescinded and rescaled by this tau n goes in distribution in probability to a n0 v0. Okay, so you see that it's the same as before, but we have this extra alpha n. So as expected, the tempered posterior has the effect that you get a slightly more spread distribution. Okay, something like this maybe. So here I already rescaled in this scale, because you will get convergence. So if alpha n is fixed, is a half, for instance, you still get rate 1 over square root n, but you lose this factor square root alpha n. Okay, so then it's natural to say, okay, so if I have, so one thing to note is then the scaling, the square root n is replaced, say as expected, by square root n alpha n. And then you might ask, okay, what happens for credible sets? So we can define, so as last time, we can look at the quantiles of the tempered posterior. So let's look at the delta over 2 and 1 minus over delta over 2 quantiles. Okay, so that's a credible interval for the alpha n posterior. Okay, and so we know that, so this result implies that it's a bit too wide. Okay, so we get it multiplied by a factor 1 over square root alpha n. Okay, so we can maybe, it's natural to think that we can say, again, shift and rescale this credible set to get something optimal. Okay, so to do that, I'll consider, so let psi bar be a point estimate built from the tempered posterior. Okay, so you can think of the posterior mean or the posterior median. So recall I denote it like this, although it's not a condition. Right? This is the notation. Okay, so I'm going to define, so think of the posterior, we'll take the posterior media in a moment, so median or mean, because it's itself a quantile, so it's easier to work with if we have a BVM type result. So we're going to set J n of x to be, so we center that psi bar, and then we multiply, we shrink. Okay, so the quantile set here will be a bit too big. Okay, and we are going to shrink it around this basis point. Okay, and delta over 2x, and so minus psi bar, comma, and the same but on the other side. Now a and 1 minus delta over 2 x minus psi bar. Okay, and result is that So suppose we have the semi-parametric type BVM, okay, so this result. And so what's important and not completely obvious is, in general, is that this point estimate you have chosen should be close enough to the efficient centering that we remember yesterday that we had psi hat, okay, plus little op here of 1 over square root n. So if we have that, then this modified credible set is also a confidence set, in that the true value of the functional belongs to this set asymptotically with the good coverage, and you can also check that it has optimal length. Okay. All right. So this is a result we obtained recently with Alice and also Collian Ray and Luke Travis. Okay, and so the condition here, which is not completely trivial to verify in general, is this one. So if moreover, so if alpha n is fixed, is equal to alpha in 0, 1 fixed, then this condition is always verified, always okay for the posterior median. Posterior median of the of the induced distribution of this distribution. Okay, so and of pi alpha n on C eta, which I did not give an x. Okay, and so that's nice, because then you can have this this modified set for free using this theorem is a confidence set. Okay, but in general, when if alpha n goes to 0, this is more subtle, because what will follow from this result is that often you have this, but with this 1 divided by square root n alpha n instead of square root n. And so this is, if alpha n goes to 0, you have to work more, and sometimes it will not be true that this is also a little op of 1 over square root n as required here. Okay, so we have an example where we show that if alpha n goes too fast to 0, this can start to fail. Okay, so it's more subtle, but as expected, right? So here we modify the posterior, so we modified the likelihood by raising it to power alpha n. So if alpha n goes to 0 too fast, we expect that we may be in trouble sometimes. But maybe the philosophy to keep in mind is that at least if you just use, for instance, tempered posteriors for technical reasons, because entropy conditions are hard to verify. Okay, recall that we proved the rate theorems for tempered posteriors only under prior mass conditions, but then, well, then you can use this result to show that you still have an optimal uncertainty quantification, provided you, okay, if alpha is a half, for instance, provided you do this modified set. Yes?
Remember what is psi hat?
Psi hat is you know, is the what I called the efficient centering yesterday. So it was the psi eta 0 plus a random term which goes to 0, which has scaling 1 over square root n. Okay, so it is. I defined it yesterday as. Let me to be coherent with the notation. Is what I.
So but in the condition star, we might replace psi hat by psi 0 then.
Sorry, say it again. So that's the definition from yesterday. So recall this is a term that goes to a Gaussian, and this divided by square root n.
Okay, I was telling nonsense. So we cannot replace psi hat by psi 0 in the start and
No. Okay. All right. So, other questions? It's a good moment, I think, before we go to the next topic.
What is the definition of the I interval?
What is the so this definition? So here it is. Those are the quantiles of this distribution. Indeed, yeah, I just said it, but didn't write it. Thanks. Yeah. Other questions? So what we have seen so far are some techniques that formalize the fact that for finite dimensional functionals, for nice finite dimensional functionals, we have asymptotic normality. We can prove asymptotic normality of the posterior distribution. Okay. So if there are no questions, let me go to, so what we wanted to do next is to try to lift this to more complicated functionals and maybe function-valued functionals. Okay, so to do so, the idea was that we wanted to, as I mentioned, maybe to see if we can get some non-parametric Bernstein-von Mises theorem. Okay. So let's see how we can, if and how we can do that. And recall the motivation we had yesterday. The practical example I gave is this example in survival analysis where we'd like to estimate the survival function. Okay, so survival function is just 1 minus the distribution function, and so we want to estimate it as a function in order to get a confidence band, for instance, which is very interesting to get also in practice. So that I'll keep maybe for now. Okay. So remember what we wanted to get is something. So here I have some. So if we know how to sample from the posterior distribution on survivals, okay, eventually would like to get something like a confidence band, okay, for S dot, okay. So equivalently, so S dot was 1 minus F dot. So in survival analysis, the difficulty is that you don't observe directly the event you're interested in, which is the event in T, but a simpler, slightly simpler version of this problem, which already captures the difficulty, is just to estimate. So that was in survival. Okay, the example I gave yesterday, but you can also a slightly simpler example is if you're in density estimation and want to estimate the primitive of the density, right, the distribution function, it will already capture so if you know how to do that, you will know. It's a bit more work, but you will know how to do the survival one. Okay, so we'll try to explain how we can do this. And it's not a completely, even in this simple setting, it's not completely obvious. So if you take the Bayesian approach with the prior on F, say, now we have a functional which is a function, okay, which is the distribution function. Okay, but so if you have built a prior on F, it's not completely obvious how you will analyze the posterior distribution on this directly. Okay, so there are a few specific priors for which you can actually characterize the posterior of this, but it's kind of an ad hoc method, really specific. Okay, so we'd like to do it in a much more generic way. Okay, and in general, it is quite difficult to analyze the posterior, or already the posterior on this. I mean, now we have seen a lot of tools to do that, but it's not clear how you would get a result for a function like this, okay, also for other functionals. So that's a bit of a motivation for the tools we are going to investigate now. So Bernstein von Mises 2. And let me draw a little picture maybe. Just before, let me say that, so the goal will be to extend BVM to a nonparametric setting. Okay, so for us, as a kind of prototypical model, we will work in white noise and density estimation just to understand things. And so there are two difficulties if you think about the just the BVM in the parametric setting, the very first one I gave yesterday. There are two things. So the one thing is the distance, what type of distance you use over distributions. So in the first version I gave, I used the total variation. But the total variation, if you are in a high dimensional or infinite dimensional space, is going to be very strong. Okay, so as I already noticed yesterday, it's actually easier to work with a weaker distance. And so that step we already did yesterday. So we already went for the semi-parametric BVM to result in a bounded Lipschitz metric. Okay, so the beta S. So we're going to use the bounded Lipschitz metric, bounded Lipschitz, which metrizes convergence in distribution, which metrizes this with convergence. And maybe also very important is that the natural spaces one can think of to estimate this are L2 or L infinity. The norms are too strong in a sense. So you can show that you cannot prove a nonparametric BVM in L2, even in Gaussian white noise, unless you take very unnatural priors, or priors that undersmooth a lot, and then the corresponding credible set would be huge. Okay, so the idea here will be we will try to weaken the norm as much as possible, not too much, but still sufficiently such that we can get meaningful information. Okay, so the picture will be like this. So here we have F, and we have our posterior. Okay, posterior. Okay, and the idea will be to embed this, to look at the posterior, but not in the original space, but to build a larger space. So here it's quite helpful that Felix has already talked quite a bit about spaces of distributions and large space, so it will they will not come as a real surprise for those who have seen this already. So we have seen this already in the past days. So we are going to consider two types of space. So an enlarged space H with an L2 type structure. So the idea is that it's a space that will be larger than L2. Okay. Essentially, it will be a space of distributions of regularity minus 1/2. Okay, and we will also want to go to a slightly different space, because so this one will be nice to work with functionals which have an L2 type structure, but this one, the topology that's more adapted is something like more like L infinity type structure. So we'll need another space which can be seen as a Bezoff space of regularity minus 1/2. And both spaces, they will be characterized by, will work only in sequence space. So it will be spaces of coefficients, sequences. And the link to the nonparametric is that from here, if we have a prion functions, we will map it to just the sequence of its wavelet coefficients. Okay? Okay, FLK, the sequence will just be the bracket F psi LK. Okay? So from there, we will get here at this level, we will be able to get a BVM. Okay, so either in H or in M. okay, in this enlarged space. But once we have done that, you may rightfully say, okay, that's nice, maybe, but what can we do with it? And if you have a BVM in an enlarged space, what you have at your disposal, since it's a convergence in distribution, you have continuous mapping. Okay, so if you know, for instance, that you can prove in some sense that this mapping from a certain space to which maps it to the primitive is continuous. So if we can give a sense to that from the M space to the space of continuous functions, then by continuous mapping we'll deduce BVMs in more usual spaces, like in or in the space C0, like for the primitive. Okay. All right. So that's the plan, and here we'll use the BVM for the nonparametric BVM tools. And why? The reason is very simple. And it's also why I insisted yesterday on linear functionals, is that here the wavelet coefficient is just a very special linear functional. Okay? Of course, you need to control them, not just one, but many of them simultaneously. But you can do that. Yeah? Yes? So it's in the notes. It's in the CF, the appendix. Okay.
Because the second one is this linked to the space that you consider, for example, if you are in L2, is there a norm involved in the definitions of the non-Lipschitz matrix? Because
yes, so you need metric spaces, and those will be metric spaces. Yeah.
okay, so it's related to the space you consider and the norms you consider?
Yeah, exactly. Yeah. So there is just a canonical definition of the bounded Lipschitz, but so today I'll not give all the technical details, but so I've put that in the appendix. So there is a little section with the typical distances between distributions, like total variation, bounded Lipschitz, etc. Okay.
Maybe, if I'm not mistaken, it's worth mentioning that bounded Lipschitz norm is transportation distance.
Yeah, you can.
It belongs to that family of.
Indeed, so you have you can express it like a soup over like test functions, indeed, which are bounded and Lipschitz. So you can indeed. It's a certain distance, and what's important is that it metrizes convergence of distributions.
Just when you wrote BVS in R, what is L2? I'm surprised that you write such a on the bottom right. It seems to be too simple. Or yes.
Yeah, no, that's indeed very simple. We don't need, so we could use this, or I mean, you can. It was just to mention that you, as long as you have a continuous map into any space, you will have a continuous mapping. But indeed, what we are interested in is C0. Yeah. Yes.
When you talk about wavelets, are you talking about the power wavelets?
So that's a good point. So one example I was about to write here is indeed. So in fact, I'm thinking about it can be a regular wavelet basis. But if you are not familiar with wavelet, it doesn't matter. Hopefully, maybe you know indeed it's good just to think about the Haar wavelet basis, okay? And the Haar wavelet basis is just defined, okay? So the first one is just the indicator, okay, of 0, 1. Then the second one will be this one up, okay, and etc. And then you have to take slightly, okay. So then they start having supports. So that's one of them, okay. etc. So the idea is that you take a dyadic partition here that you make finer and finer, and the important, so you get psi lk. So the first one is going to be the indicator, and then you define them by scaling and shifts of from the blue one. Okay.
So this basis is sufficient for your purpose?
Yeah, you can use indeed the wavelet. For most purposes, it will be enough. So what you will not get with a Haar wavelet is a high regularity. So the problem is that if you want the full picture, like if you want the posterior rate result with arbitrarily fast rates, you will need smoother wavelet basis. Okay, so but for instance, to do that, you can use already just the wavelet basis. It's just that if you want rates that are, for instance, the optimal rate. So suppose you want to do density estimation with an optimal rate for f, then you'll need to use typically a smoother wavelet basis. Okay. Yes, so if you are in the density estimation case on 0, 1, you will need things like boundary corrected wavelet basis, for instance, like Cohen-Dobschi Vial type basis. Okay, so I didn't want to go, so I don't define them actually in the notes, but that's a good point that I mean all questions were good just to clarify a bit the setting, but again. A bit similar to, I mean, I don't give all the definitions, but you can just think for our purpose for our purposes of the Haar basis. Yeah, sure. Okay, so one thing that will be important and that we will use is that it is a localized basis. So it's immediate to see from the definition that if you are at a given level, okay, so if here, so I'll draw it with little dots. Okay, so that's the second Haar wavelet at level 2. If you take the absolute value and you sum, then you just get, you see that you just get 1. So here, the sup norm of this, it will just be equal for the Haar, but for a more general wavelet basis, it will be of the order 2 to the L over 2. Okay, because here, this thing here will have it will be like 2 to the L over 2 psi 2 to the L minus x minus k. So it's defined like this from the first wavelet. So the sup norm here of psi lk is just 2 to the L over 2. Okay. And so what's important is that at a given depth, for a given L, if you take the sum of absolute values of the wavelets, you stay at the same level as the sup norm of one wavelet. Okay, so that will be that comes in later, and that's the reason why we use wavelets, is that it's nicely compatible. For instance, if you want to prove things in the sup norm. Okay, more questions? Okay, so let me now go to, so very briefly, I'll explain, because the space is a bit easier to define, I'll explain this, but since the main application we have in mind is rather this, I'll move quickly to this. So again, I apologize for not giving too many details, so sorry that I didn't write all the expressions on the board, but I just want to give the intuition, and hopefully everything is in the notes if you want to have more details. Okay, so for instance, so the bounded Lipschitz metric, we will not use it directly here because it is within a theorem I will not show here that its definition shows up. Okay, I mean I will show the theorem but will not prove it. Okay, so the Gaussian white noise model and the H space. So, as I said, what we want to do is to define some space of which, as I said, I view now the functions as sequences, the sequence of wavelet coefficients. And the reason why I do that is that the norm becomes, so if you enlarge your space, the norm becomes weaker. Okay, so let me write the norm. It's just a sub-F norm. There is a slight technical thing here that we will weight it. It will be a logarithmically weighted negative sub-F space, if you wish. So square FLK squared is finite. Okay, so S is the regularity, and delta is just the, as it shows here, delta is just a small logarithmic correction. So you may be more familiar with the definition with, say, thinking of the Fourier basis instead of a wavelet basis. And the only difference is that with wavelet, you have double summation, and Fourier, you have only a summation over k, and the 2 to the L just becomes k. So in the Fourier domain, this would be, maybe it's a bit more familiar, but the reason why I could actually do this with Fourier basis, but we will need wavelets for the M space. So I thought I'll go directly to the wavelet notation, just to have one fixed basis. Okay, so in the Fourier domain, it would be something like this, k to the 2s fk squared. Okay? And here with wavelet, the k is replaced by this 2 to the L, and we have the multi-index summation. Okay, and the space we are taking will be this one, so H2 minus a half delta. And so what is the intuition of taking this space? Well, when you take S negative, you weaken the norm, and it's not difficult to see that, in fact, so let us write our Gaussian. So now when I say Gaussian sequence model, a Gaussian white noise model, I take immediately the projection into sequence space, and now the sequence space means with respect to the wavelet basis. So I have two indices, okay? But it's the same. Before I was writing xk equals fk plus epsilon k over square root n. Now I just write the same, but in multi-indices, okay? Okay. And it's not hard to check that, in fact, if you look at this norm, minus a half is exactly the place where you start having a parametric convergence rate for estimating f. Okay, so the non-parametric typical rates of estimation, they are much slower than 1 over square root n. But if you weaken the norm, there is some point. If you make s smaller and smaller in the negatives, there is some point where you reach 1 over square root n, and this point is exactly minus a half. And the slight correction here is just to make the series convergent, and it will show up. So now if we want to verify that this equation can be written in H, so we can do that. So let me write xk with a bar, sorry, without index, x with a bar equals f plus w bar over square root n. And I claim that I can write it, I can view it in H. So here x bar is just xlk, and f is flk, okay, and w is the collection epsilon lk, okay. And here I didn't say what delta is. Delta is just something larger than a half, just to have some ability. Okay, so let us check that, in fact, W is in H. So if I take the expectation of WH square, I just get the sum over L, sum over K of what? Of, so L minus 2 delta 2 to the 2 LS, so S now is -0.5, so minus L, and F, and now expectation of the Gaussian square, okay, which is 1. And since I have 2 to the L wavelets here, I get, so this is equal to the sum over L of L minus 2 delta, sum over K of 2 to the minus L. So if you think of the R basis, this is just 1. And so this is finite as long as delta is larger than R. So it means that I can see read the white noise as something in H. Okay. And so then a natural way to define BVM, nonparametric BVM, is just going to be to state it in H. Okay? So I have now a prior pi on L2, okay? Which is, or on little L2 if you wish, here. And this will give me a posterior, also sitting on L2. And I can view it just by embedding L2 into H as a posterior on H. Okay, so that posterior on H, I'll denote just to insist that it's on H, but I could still denote it this way. Actually, in M, I will just use this notation, but just to insist that I'm on H. The posterior on H, I'll denote it just to insist that we work on H with like this. Okay, and well, as before, we are just going to introduce this shift. So from H to H with the scaling square root of n. So to Z maps it to square root of n Z minus a certain, F. So if I were centering Z, so I centered at Z for some Z in H. Okay, which will be the centering. So here, actually, the efficient centering is just this collection of all XLKs. So it's, so I denote tau index subindex Z, where the Z is the shift. And we are going to say, so definition. So the nonparametric BVM holds in H if so the bounded Lipschitz metric in H between the posterior, so I'll write this as a pi n as a shorthand for the posterior, or well, yeah, pi, okay, I circ tau minus 1 of x. So I just recenter by x and multiply by square root n. Between this and a certain n, which is just the distribution, the law of the white noise, W in H, this will go to 0. So if this goes to 0 in P0 probability, I said that the nonparametric BVM holds in H. Okay? So well, I'll remove this to have a bit more space, but so recall that here, what I was just saying is that we can get an asymptotic control on the Laplace transforms. Okay. So once you have convergence in distribution, okay, so I just use bounded Lipschitz just to as a distance to express that Mitra convergence in distribution. Once you have convergence in distribution, you can have things like portmanteau lemma, but of course here we are on a bigger space, but we will have a similar result, so I'll not go into the details again, but you can show a bit similar to portmanteau here, that if you want to consider a credible ball in H, so the first application we gave of the BVM in a parametric setting was that credible balls are credible intervals are confidence intervals. Okay, so similarly here, the natural analog of interval is just a ball. So a ball in H, a credible ball in H, would like to say that it's a confidence ball in H in the frequency sense. Well, this is true, and the reason is because the limiting distribution, so this white noise, it will not charge the the sphere in H. Okay, so for portmanteau lemma, you in order to pass to say that probability of xn belongs to A goes to probability of x belongs to A, you need that the limiting distribution doesn't charge a boundary. And here you can prove there is classical results showing that for Gaussian measures you don't charge the boundary. Okay, so I don't prove this, but let me just give the application just to fix ideas that indeed we can do things similar, say things as usual, except that they are in the large space H. Okay, so say as usual we can kind of define Rn is such that pi of Cn given x is equal to 1 minus alpha, say, okay? Or if this doesn't have a solution, you take a generalized quantile. Okay, and you can show, I'll not prove it here, that goes to 1 minus alpha. Okay, so the credible balls are confidence balls, okay? But of course, that's still a little bit abstract, okay, because the space H is very large. So there are ways to remap, and then you'd like to remap this to more usual spaces, okay? So since I want to discuss more this f dot application, I'll just mention that, but that there are ways to remap to a confidence set in L2. And the idea is just that you intersect this very big set with some much smaller set, and then by interpolation you get something in L2. Okay. So do I want to say much more? I don't think so. Maybe just briefly mention that, but I'll state a result in the M space, but just to say that to prove a sufficient condition to prove a BVM in H will be just to show two things. Is a bit like usual with processes. So you show that finite dimensional distribution converge. I'll make the statement formal for the M space, okay? But I just give the idea, and plus a tightness condition, okay? Tightness plus convergence of finite dimensional distribution. That's kind of should sound a bit familiar if you have done some convergence of processes, okay? So that's the same happens here. Okay, so I'll not insist too much on the H space, but you have several applications. I mentioned some in the notes. Let us go now to the M space. Okay, so that was just to give the idea. The idea is that you just define an enlarged space in such a, with a norm which is weak enough in such a way that you have a square root n rate. Okay. So, but you have, of course, several ways to enlarge the space. Okay, so that's just one possibility, and another possibility is to define things not with an L2 structure, but something with the max of coefficients, something more like related to base of spaces. Yes?
I have a question about this confidence term that you appeared. So
Yeah.
can you be specific about what you mean by the confidence set in L2? Because we're working in this bigger space now.
Yes, so that's why you're right. So you want to remap this into the more usual spaces, okay? So this is purely in H, and then you have to work, if you want to be back in L2 or in the usual spaces, you have to do something. And what you can do, but I didn't have much time to explain this, but what you can do is that you have this very big set, you can intersect it with a small set, which here will be actually, so will be a norm in a much stronger norm. So if you are able to show that the posterior concentrates with a even very slow rate, but in a stronger norm, you can work with the intersection, and you can show that the intersection is indeed back in L2. That's a bit the idea. But here I'm not proving anything in this vein. I'm just giving the idea of that and telling you to believe me that you can do something like this. But okay, so here what I just want to say is that if you do the standard thing, you take this ball credible set, it can be shown just by tools of convergence of distributions that it is also a confidence set. And you have reasons here to say, okay, is this confidence set useful because it's in a very large space? Okay, I guess that's your question, right? And what I'm just telling you is that there are ways to remap it to the usual spaces, but you have to do something. You cannot work with this very big set. You have to intersect it with, for instance, you can intersect it with a smaller set and then try to prove things.
You don't have a BVM in L2, but you can
No.
look up the...
Yes. So here I could have decided to present you only things here, and we could have looked at this, but I preferred to show you things here to get this application for this functional application. Okay, so you'll see this what you call the cookup. The cookup here will be, there will be no cookup. I mean, we'll just be applying continuous mapping. Okay, but you're right that here it will be a bit more of a cuisine because you have to do something to the set. You cannot apply some generic principle like continuous mapping. But here you could also have applications with continuous mapping here, which I mentioned in the notes. But yeah. Okay. Other questions? No. Okay. So now we are going to see if we can define some nonparametric BVM in a space similar to this one, but with a slightly different structure. It will be a set M. And here we'll consider density estimation. You can also do it in white noise, of course, but since I have this application with capital F in mind, let me work directly from scratch in density estimation. So P F a set of densities, and F is a density on the unit interval, as usual, very, very simple. Okay, and I'm going to denote PF, not subscript, but just PF is just the usual notation, like a bit operator notation for integral FdP. Okay, so let me keep for now the definition of the H space. Okay, so what we want is, so since we said, okay, we immediately go to sequence space, okay, so we identify a function with its wavelet coefficients. Here, let me do, here it was very easy to have an estimate of FLK because you just have observed signal plus noise, okay? So here a natural estimate is just, say, F tilde LK equals XLK is actually an efficient estimator of F in H. So here in the density estimation model, so in density estimation, so it's very easy. So if we want to estimate a wavelet coefficient, since it's a linear functional, okay, estimate FLK, F psi LK. So what can we do? We can just take an empirical, okay, Pn of psi LK. We can just take this, okay? And now we'll have a convergence in distribution because this is not Gaussian, okay? But in the limit by the CLT, it is Gaussian, okay? So here we had already automatically that if I recenter by FLK multiplied by square root n, it's already perfectly N01 Gaussian, okay? Here it's a bit more complicated, but not much more, so we just use the CLT. Okay, P. This goes in distribution to a Gaussian centered and with variance the integral of psi LK minus P psi LK squared 0 and 1, because I said I work on the unit interval, dp. Okay, so this is a certain sigma, certain variance, okay, which may depend on the wavelet, which depends on the wavelet basis you've chosen. Okay, so it's a certain sigma lk squared. Okay, and what I'd like to define is a kind of a Gaussian, a bit like a Gaussian limit experiment like this. So I'd like to identify now the limit in BVM. What is a natural limit in BVM? So natural limit in BVM is, so since my function is a collection, I identify it to the collection of its wavelet coefficients, I want to define a Gaussian object which would be the collection of all the Gaussian limits over all coefficients, okay? So this is exactly trying to identify this limit. So this suggests, so this here suggests defining a Gaussian process, so a centered GP, okay, which we'll call G bar P, indexed by L2 of P, with covariance. So I define it really in a similar way as you would define white noise. So here the limit is not white noise, it will be just something slightly perturbed, whose derivative will be a Brownian bridge, okay? So like here, the derivative of white noise is you can see it as Brownian motion. Here, you want to get Brownian bridge. Well, it turns out that you'll get Brownian bridges. For the moment, there is nothing. But so we will call this white bridge, and it's just a process such that you just want to match this. So if I have two functions arbitrary in L2, like in particular the wavelet coefficients are special cases, this will be, this I define as, so it's essentially, it's almost the L2 inner product, but I recenter. Okay? I recentered, okay? So that I get this formula. So if G equals H equals psi LK, I get this formula. So this, call this the white bridge. So we didn't know a name actually, so we thought it was natural to call it a white bridge process. Okay, or P white bridge because it depends on P. Okay, and so that is kind of seeing what the limit is going to be, and now I'm going to define the equivalent of the H space. So the M space now is going to be just a norm which is a little bit more compatible with this C0 or L infinity structure. And it will be, you can see it a bit as a Bezov type norm if you know a bit of Bezov spaces. So M, so I'm going to take a weighting sequence W, which is a bit the same as this L minus delta. So WL will be some sequence going to infinity. So MW is just the set of sequences such that, so the norm XM, so I replace the sums by sups essentially. Sup max, so there are a finite number of k's for a given depth of the wavelets. So something like this. Okay. XLK divided by WL finite. Okay. So that's the M space, but actually will not work exactly with this space because it's not separable, because it's, you can think of L infinity. Okay, so we'll work with a slightly smaller space, which we denote M0W, which is just the sequences such that instead of being finite, we go to 0. So limit, and that you can show that it's separable. Limit in L, max in K, XLK over WL goes to 0. Okay? So if we now look at GP, so recall that what we want to do is define this process. So we have defined this process here just on L2 of P, but what we want actually is just to test it against psi LK. So we want to define, we have this process on L2 functions that we just look at wavelet coefficients. So we just look at GP psi LK, and we can ask, does this belong to M0? Okay, so now I'm doing a bit the same calculation as before, where I checked that the W here belonged to this space, okay, for appropriate choices of delta. Here it's the same. Okay, so I'll not do the complete proof, but just a few lines. And the idea is that since this is Gaussian, it's easy to control a max of Gaussians. Okay, so we can ask this, and this is going to be yes, provided W, the sequence W is well chosen. Okay, and how do we see this? So if we look at max over K of GP psi LK divided by WL, so the WL I can put in front. So this max, since the sigma LKs here, they are bounded, okay, because here, so this will be dominated by the integral of psi LK squared, okay, and this is also of the same order. And if the density here is bounded, which we'll assume, then this is going to be bounded, okay. This is bounded by some C. Okay? So if I have Gaussians with bounded variances, then this will be of the order of the square root 2 log of the number of Gaussians. Okay, so there is a constant here which depends on this constant, and here I have 2 to the L coefficients. Okay, so 2 to the L. So this is of the order square root L. Okay, so now you see that if WL divided by square root L goes to infinity, then it is fine, okay, because we'll be in this space. Okay, so that's just a sketch proof, but it just uses the maximum of Gaussians. All right, so now we can just define nonparametric BVM in the same way we did for H. We just say, okay, suppose we have some centering. So there is a bit of work for the centering, and I will not tell you, well, I can tell you what we take, but I'll not worry too much about it. We can come about that later. I'll just define it with a given centering, okay? So, all right. This we discussed, okay? So as before, I take tau a shift. So F goes to square root n F minus Tn, and I define Pn tilde will be the posterior circ to tau minus 1. Okay, so here I embed, as before, I embed the posterior in the M space, and then I apply this transformation. And I didn't take a different notation as I did before, I just take the same. Okay, and I define N to be the law of G P0. So P0, recall, is just now the density. I have a true density, so P0 is just PF0. And so, okay, the law of GP0 so here it's, well, I have to be a bit careful. Let me do it this way, okay, and law of G in M, in the M naught space. Okay, so we say that the nonparametric BVM holds in M0W if I have that, so the bounded Lipschitz metric in M0 between pi n tilde and n script, this new n now, goes to 0 in P0 n probability. Okay, so let me actually, I'll just prefer to write it this way. I prefer to keep P0 for P f naught tensor n, and here I just note Pf0. Okay, so that's just the natural definition. And now let me give the formal statement to prove this. So this tightness plus finite dimensional distribution convergence. And then we'll see how we can use it. So I'll say, okay, so we have a proposition. Okay, so suppose, so in order to verify this, it's enough to have two things. So the first one is a tightness type result. So the E, so we need that. So we need some centering Tn. So here I centered by some Tn, which needs to belongs to M naught. Okay. M naught. This, so which is the, again, this norm. So I'll write. I take a smaller space, but I still take this norm. So let me write it. But now I need a W bar. W bar, which is slightly slower than the W. So this given X has to be a big O pedant of 1 over square root n. This is a big O here, okay? All right, and W bar, I'll say in a second what it should verify. First thing and second thing, we need finite dimensional distribution converge. So meaning that, so if I just have one, so I'll state it slightly informally, one given wavelet coefficient, okay, for a given capital L and capital K, I want that this goes to 0, goes to a Gaussian 0 sigma, my sigma of before, sigma capital L capital K squared. Okay, so that's for a given LK, so I want that, but I also want that for any possible collection, for any finite collection of FLKs, okay? So where L belongs to some finite set L1 and K. Okay, so just some convergence of finite dimensional distributions. Then, if we have that, if WL over W bar L, so this one goes to infinity, so you need just a little extra space, but it's fine. Generally, if you take WL to be a little bit faster than square root L, like L a half plus delta, it's enough that you take L a half plus delta prime with delta prime smaller than delta, okay? For your W bar, that will be true. Then we have that the BVM holds in M naught, okay? Pi n tilde, n goes to 0 in probability. Okay, so that's just a little proposition showing that what you need to verify. Okay, so now the question is, how do we check both things? So there is one condition which is which should look a bit familiar. It is this one, okay? Because this one, this is nothing but a linear functional, right? So that's what I wrote here on the board, suggesting this. So to prove this, you use the tools of yesterday, okay? So the semi-parametric tools. All right, so what's more delicate is this, because this is a convergence of the posterior in what I could call multi-scale norm involving maxes. Okay, and so we don't really have tools yet to handle this, because in the first part of the lectures we saw tools for testing distances, and if you have a distance for which it's not clear whether test exists, okay, for that distance it's not so clear whether you can construct tests as in the GGB theorem, so you have to do something else. So I'll come back to that in a moment. So are there questions before we go to the application with capital F? Okay, so that's kind of abstract, but we want now to, so this will be helpful if we want to get results for functionals like capital F. And now let us see why capital F is a nice functional from the M space to the space of continuous functions. So if it's the case, if we have convergence in distribution in M, we can deduce convergence in distribution in the space of continuous functions for capital F. Okay, so and I'll come back to that later. Application, Bayesian-Donsker theorem. Okay, so the idea is really now we want to go back to more usual spaces. So theorem, which is 6.8 in the notes, I think. So in density estimation, so let pi be a prior, as usual, like one of the priors we took in the first week, for instance, on continuous functions. So you could think of, say, Ronan motion exponentiated, or some other prior on continuous functions. So here, continuous function is not really essential. I mean, you could take a histogram prior as well. And suppose two things. Suppose the nonparametric BVM holds in M naught W, okay, with, so we'll ask something about W, which, so what will we ask? WL such that a certain summability condition is verified. So here we have some space. We can actually take WL. So WL helps us. And why? Because it's reweighting our space in the good direction. It's making so the bigger the nicer. So okay. So we have some space here, if we want, and centering Tn that belongs to L2. Okay, so we need, so it belongs in principle to M naught, but we also assume that a bit more that it belongs to L2. So define, so f of t equal to the primitive, okay, so this capital F map, and so since Tn belongs to L2, I can define a T bar n equal to, again, the primitive of Tn. Tn of u du. Okay, and let also G be a P0 Brownian bridge. Okay, so now we have in a sense to take the derivative of the G, so it turns out it is a Brownian bridge. Then, so we have two things. We have what we wanted at the beginning, so the distribution of square root n capital F minus this centering, given the data, the bounded Lipschitz metric between this and the law of the Brownian bridge, this goes to 0 in P0 probability. And also, so as usual, like when you do Kolmogorov-Smirnov, you can just take the soup norm, so the law of f minus Tn soup norm given x goes to the law of the soup norm of the white bridge, of the Brennan bridge in P0 probability. Okay, goes to 0 in P0. Okay. So that's nice. So let's see why it's the case. And to prove this, we essentially will need to show that we have a continuous map from M to the space of continuous functions. So the map will not be defined. So before we check the proof, are there questions on this? Okay. So now, since we start from M, in principle, this is not defined. Okay, so we have to be a bit careful with the definition of the primitive. So the proof. Okay, so we define the map L from M0W into say, L infinity. In fact, you can check that you can take C0 also as well. But I'll just check the L infinity here. It will be enough. HLK, sum LK. So here I have a little formula, which we'll see in a moment. In fact, it's just, it will coincide with the primitive map if the functions are in L2. Okay, so psi LK is my basis, so I can take the primitive and I do this. Okay, so let me check that this map is, so it's a linear map. Okay, let me check that it's continuous. So I take the absolute value. I want to show that for any t, the absolute value of this is bounded, okay, by the M0 norm of the H sequence. Okay, so that will be, that's where we will need we are going to need the localization of the wavelet basis. So why is that? So we'll see in a second. So this we bound a bit like we do also for soup norms, sum over L. Here I can take the max over K of H LK. Okay, and here I still have a sum over K of what? Of those things here. And this is just the bracket psi LK indicator function. Okay. This is, here I just put, so psi LK indicator 0t. Okay, so I have a double sum here. I pull out the sum in L, and I replace within the second sum in K. I bound the HLKs by the maximum. I pull it out of the sum in K, and I'm just left with this. Okay. So now that's where the localization property is helpful. So you can show that this is actually in general for a localized wavelet basis, this will be smaller than 2 to the minus L over 2. So let us check that for the Haar basis. So the reason is very easy for the Haar. For other wavelets you have to work a little bit more. But for the Haar basis, if you look at this sum, so what's nice is that so the Haar wavelet basis is defined with these functions like this. Okay. So with like if I have a value m here, I have minus m here. Okay. So most of the time this is going to be 0 for a fixed level L, except when I encounter the jump here, and this can be non-zero only if I encounter the jump. Okay. So because if you think of this function like this, so actually I should write it to the right hand side of 0. So if you have a wavelet function, a Haar wavelet function like this, okay, so if my indicator is going to be like this, right? So for all those wavelet functions whose support is completely contained in 0t, I get 0, because the integral of the psi lk, except for the first one, is 0. Okay, and to the right, the same. So I only have a non-zero value if I, so actually I should, the value is bigger. I only have a non-zero value if I intersect kind of this jump, all right? So for the Haar basis, there is actually only one term active in this sum, and for any term in the sum, actually, psi lk indicator 0t is always smaller than, say, the L1 norm of psi lk times the sup norm of the indicator, which is bounded by 1. Okay, so this is bounded by 1. And the L1 norm of the wavelet, of the Haar wavelet, is just 2 to the minus L over 2. So for the Haar wavelet, this is actually equal to 2 to the minus L over 2 because there is only one term active. Okay? And so far so good. So then I just need to introduce further the W sequence. So this says square. So square is upper bounded by, so I will introduce here WL, so WL minus 1, and then I have to multiply by WL. Okay. So what I get in the end is I get a sup over L and K of WL minus 1 HLK in absolute value. So that's the term that I pull out. And then I still have the sum over L of WL and 2 to the minus L over 2. And that we said that it converges in the, assume it converges, okay? And here I get nothing but the H, the norm of H in M naught, in M, if I want, okay? But H belongs to M naught. Okay, great. So now the only thing that remains to be checked is that we indeed, so we have a posterior, by assumption it will sit on continuous functions or in L2, okay? And I just need to check that then this map, capital L, I need to check two things, so that this map, capital L, if I have a function in C0 or in L2, it coincides with the usual primitive. And also, I have to identify this limit as the Brownian bridge, so that I'll just, I will not do that, but you can just check that the RKHS coincide. Okay? So let us just check that L coincides with the primitive map. And this is almost immediate. Okay, on L2 or on C0. And the reason now is because, so what is L? L you can view as sum Lk of HLk. So HLk is just H psi Lk and indicator 0t psi Lk. Okay? So if H belongs to L2, this is just Parseval, right? So by Parseval, this is just H indicator 0t, okay, which is indeed the primitive. Okay? And then we check that L of GP0 is equal in distribution to the law of G. Okay, the P-Brownian bridge. Okay, so that concludes the proof. And once you have this, as usual, you can take, for instance, if you have the sup norm, you can take a confidence band now, because if you take a bound like this and you take the Rn of x, like for the credible set before the Ball credible set, Rn of x such that the posterior probability that this is more than Rx is equal to 1 minus alpha, then you can show that you get, this is actually a confidence band, okay? All right, so, yes?
So
What is the interpretation that we get a Brownian bridge instead of a Brownian motion?
This is similar to the Donsker theorem, in fact, because so it's a Bayesian version of the Donsker theorem, where when you have if you think about the usual Donsker theorem, in fact, you have you get the empirical distribution function, and since you have to recenter by the central limit theorem, this minus the centering that you have in the covariance of the process, this makes it that you have to kind of so if you wouldn't have this recentering, you just get white noise, okay? And here with the recentering, we get something that we call the white bridge, and it is which makes the Brownian bridge. In fact.
The recentering.
The recentering, exactly. So it's the same. So if you are not in the Bayesian world but work with the empirical distribution function, you have the same result for like the Donsker theorem says, and it's similar, right? You have this recentering by P, which makes it different from scaling in Brownian motion or something like that. Okay, so let me see. We have a few minutes. So I have a few minutes to tell you, okay, what do we do? So there is a missing piece here, and the missing piece is, so we need not only so that gives us the finite dimensional distribution. So finite. Okay, but we also need here posterior convergence in multiscale norm, or if you want, in M norm. And that, in principle, we don't know how to do, okay, for now. And that's where this thing about the control on the Laplace transform will turn helpful. So let me see. So I mentioned briefly in the first week rates in the supremum norm, and I said that it was kind of much more difficult because you don't have the tools of the GGV theorem, because the sup norm can actually show that you don't, it's very hard to, in some sense, it's not a testing distance in the sense that you will not have exponential convergence to 0. Okay. There is a kind of a fundamental impossibility there. So, so we want a posterior rate for either the M naught norm, okay, the M norm, okay, which is the sup of max. So here there's a WL minus 1 of FLK, okay. And actually, since we are there, since it's there are sups and max, let's just look at a stronger norm. The supremum norm. Okay, so if we are able to do things in the supremum norm by the same techniques, essentially we'll get results for this. And so how can we bound? So just to show you the relationship, there is a classical bound, which is this one. So L over L and K, sup norm. So this is smaller than the sum over L. Max over K, a bit like we did before. FLK times the sum over K, psa LK, sup norm. Okay? And by the localization of the wavelet basis, this is at most 2 to the L over 2. So you have a bound of the sup norm, which is, again, involving some max, okay, of terms. And now DID, so how do you control this? Well, this is actually a semi-parametric functional, right? And we noticed at the beginning of the lecture today that not only do we have BVM, so proved by convergence of Laplace transforms, but we also have actually a sub-Gaussian bound on this quantity. So I didn't, you have to look at the examples, of course, and you have to work to show this, but just to give the idea, we'll need only a sub-Gaussian bound on this, non-asymptotic one, and you need to control this uniformly in LNK. But once you have this, when you look at this, so if you want to control the posterior distribution, the descent of the posterior, if you know, so that's actually not completely true. You have typically to restrict to a certain event on event n. Okay, so if you have a subgaussian bound on an event n, you just have to control this type of things, and max of subgaussian variables, they are easy. Okay, so we know well how to control them. They will be like square root of the log of the number of variables. So therefore, you'll be able to control the posterior also in this type of norms. I had thought maybe I will just show a little calculation, but it's really the idea is really there, and the calculation is in the note. In the notes, maybe I'll say a word on that next time. Let's see, tomorrow perhaps, or not. You just so if you think just of, for instance, of a uniform wavelet prior in white noise, you can really carry this through quite easily. So that's one illustration. And if you are not in white noise but in a much more complex model, it doesn't matter in principle, as long as you have the tools to control this, and that we saw yesterday. And as long as you refine them to have subgaussian bounds, you can also control this type of quantities, and therefore you have controls on this norm, and then you can go to there. So this program we have now carried out in a number of examples, including the models I mentioned yesterday, in particular survival analysis models. Okay, so thank you very much. Yes?
I have a question about the Bayesian bootstrap theorem. You said that it implies that some credible sets are confidence sets. And do you have any way to calculate this credible set or approximate them?
So yes, so that's a good point. So in practice, what you would do is plot. What people do in practice is they say, if I can sample from my posterior, I will just draw many posteriors, and then I take, say, the 95% of them that are closer, say, to the posterior mean or to some other posterior aspect. Okay, and you have this kind of spaghetti plots, and then they take the band that corresponds to the interior of this area where the 95% sets are.
For example, if x is the parameter, for which x they take 95%?
No, so they do that functionally, so they don't do the marginal one. You could do the marginal ones as well, but they do that, I mean, really, if you want the Bayesian spirit, you keep really the full curves, and you just take, and so that's what people do in practice, okay? So then so from this you can deduce a confidence set, a theoretical credible set that will be also a confidence set, and then if you would want to go the full way to show that what people do in practice to verify this, you still also have to check that this rule that you take the 95% of the curves, it's indeed something that comes close to the theoretical one that's here. So that there is an extra work that needs to be done also, yeah.
And when you take the bound that the 95%,
Yeah.
what the hell?
So you just suppose you so for instance in the F example, so you draw many plots like this, okay? And suppose you also have, like, for instance, the posterior mean also here. Then you would just take, you can, with the computer, just compute the sup-norm distance between each draw and F naught bar. And you only keep those of the white samples, the 95% of those that are closest in sup-norm to the yellow curve, okay? And that will give you a certain region, that is this interior of this region, which is something like this. So that's something that people do in practice, okay? Or something else they do is also take the marginal, you can also take marginal sets, but in this functional sense, it's more natural to take this approach, I think. Yes?
So I guess I think the conventional wisdom is that there's no generic infinite dimensional Bernstein-Vermees phenomenon, right? So everything you presented sounds really good. So I guess what is the technical limitation to closing this gap?
So what happens here is that we weaken the loss function quite a bit. So we, in a sense, we don't get everything for free, right? So what we have to pay is that we weaken the norm quite a bit, and we at the same time we enlarge the space. So what you can ask is that any good? Because you could think, okay, then the space is too large and this is useless. But what I've tried to show you is that even in these very, very large spaces, you can remap things by continuous mapping to usual spaces, okay? So it's enough to work in these spaces, although if you don't want to make this weakening of the norms, there are ways to show that, I mean, it's not possible really to have the full thing that you would get and in a sense it corresponds to the fact that you don't have efficiency theory, for instance, in nonparametrics and things like that. Okay. Well, if there are no more questions, we can maybe have coffee.